Hello everyone. Welcome to the first lecture of the third module, which is on dynamic RAMs or DRAMs. The disclaimers remain the same. So we were basically looking at 60 SRAM cells. We were looking at how we do this read operation. That is, we precharge BL and BL bar, and then we, kind of assert this word line high, and we see how exactly this read operation takes place. And for read, we found out that your NMOS transistors of the inverters have to be stronger than your access transistors. Similarly, what we found was, for a successful write operation, what we want is our PMOS of these inverters should be weaker than the access transistors. So this led to a read-write conflict, and to resolve that conflict, how we size the different transistors in a 60 SRAM cell is, what we do is we simply take the size of this PMOS as least, or the strength of PMOS transistor as the least. Then we make the access transistors more powerful than PMOS, and we make the NMOS transistors most powerful. So as a consequence of this, at the end of the day, our 60 SRAM cell inverters are not symmetric. And by symmetric, I mean that the PMOS and NMOS there are not exactly matched in terms of cooling strength. Okay, so after this, we also looked at the different sources of the different noise margins and all for the 60 SRAM cell. First, we looked at this hold static noise margin. So during the hold operation, what we saw was that the effective circuitry of this 60 SRAM cell gets reduced to a cross-coupled inverter pair. And then this hold static noise margin is simply, if you introduce, two noise sources with opposite polarity. For instance, let us introduce one noise source here, one noise source here, and they have to be of opposite polarity, right? So if it is minus and plus over here, so it has to be plus and minus over here. So this represented your worst case scenario. And if you have this kind of noise in your circuit, this noise source can be the power supply, it can be thermal noise or any other such offset as well. So because of this noise sources, what we found out was that in this butterfly curve, which is kind of representative of this bistable element without any noise, if you introduce these noise sources such that the magnitude is kind of equal to the hold static noise margin, then we saw that instead of these 3 intersection points, we ended up with only 2, right? And we discussed that if we further increase the noise beyond this magnitude of HSNM, that is, if we increase this Vn than this HSNM, then we would end up with only one intersection point, and that has to be the opposite state. So that has to be the opposite state. So and we also told that how we measure this hold static noise margin is, we kind of try to find the size of the maximum square that can fit inside these loops. So this is how we characterize our hold static noise margin. So for finding this VTC, we simply apply an input here, check the output over here for the first inverter, that is for the inverter 1 and inverter 2. And for the second inverter, we apply an input over here and check the output over here. So this was what we discussed about hold static noise margin. After this, we also discussed something about the read static noise margin. However, we also knew that during the read process, the situation is somewhat different. So during the read process, your circuitry is somewhat different. It's something like this. You have these nodes connected to VDD because of precharge. Let's say this is M5, let's say this is M6. This is like inverter 1 and this is inverter 2. So during read, what we found was, if we kind of, apply our inputs over here and check the output over here for inverter 1, the VTC that we got was something like this. So it started at here itself at VDD, but it went only till a point which is Vx, which is kind of, this Vx is arising because, this potential is kind of, when this, this input, that is, let's say Q is VDD, then this NMOS turns on, and this M5 and NMOS of this inverter 1 kind of, forms a potential divider pair, and Vx is kind of, the potential given by, let's say, Rm1 by Rm1 plus Rm5 times this VDD. So this is your Vx. So that potential divider kind of a thing leads to this Vx. And similarly, if you apply your input over Q bar and see the output at Q, you'll find a similar situation for inverter 2. So if we represent the VTC of inverter 2 by a different color, you'll see that, you'll have something like this. This will also end up at this point, and this would be kind of Vx. And this would be Vx because both inverter pairs are symmetric, or they are matched. So here we saw that the size of the maximum square that can be fitted inside these lobes reduced. Reduced as compared to what? So if we had this whole static noise margin thingy, if you make the whole static noise margin, so your VTC would look something like this. It will end up here, and here also it will start like this and will end up here. So if you compare the size of the maximum squares that can be fitted inside this lobe, let us draw this by green. So we found out that whole noise margin is kind of higher as compared to the read noise margin. So this is what we found out, right? And then we also concluded that your read process is like more sensitive to noise. And we also found out that this RSNM is something which is kind of hindering your scaling of SRAM cells. Why so? Because as you reduce your VDD, what happens is, your RSNM is also reducing. So once your RSNM reduces, the kind of margin that you get to play with the noise, or the ratio of your noise to signal, or the ratio of your VM, that is your maximum noise that your SRAM can tolerate during the read process as compared to the VDD, that increases a lot. Or in other words, the SNR kind of, the signal to noise ratio kind of reduces a lot. And because of that, scaling becomes a problem, apart from the static leakage that I was discussing from day 1. So, okay, with this, we also then studied about, this writability. So writability simply gave you, the strength, or I would say, how easy it is to write a particular value to your SRAM cell. So that is what was given by your writability. Okay, so how we characterize it? We characterize it by, the crossover of, let's say, we represent Q and Q bar like this. So first we actually rammed, or provided a slope to our VPL like this, and then we saw how Q and Q bar are actually reacting to this. So let's say if Q was initially 1, so it will kind of, and we are writing Q equals to 0, so it will go something like this. And similarly, your Q bar will go something like this. Then we found out the instance where this VQ is equals to VQ bar, which we called as the trip point. So why is it called the trip point? Because when we reach this value, we are sure that we are going in the right direction, and we'll flip the state of the existing SRAM cell. So that is why it is called the trip point. And at the trip point, what we did was, we just kind of measured the difference between this VDD and the value of VBL at that point. And that we named as writability. Okay. So with this, we also discussed about the peripheral circuitries which are present. So we discussed in brief about SRAM cell. Sorry, about the sense amplifier. So sense amplifier is nothing, but it's any amplifier which kind of amplifies a small kind of change in your BL or BL bar to a large change so that it reaches any of the rail outputs like VDD or ground. So this is the role of your sense amplifier. Then we also discussed whether it is needed for functionality or whether it is just for accelerating the process. So sense amplifier is just for accelerating the process. Accelerates the read process. It's not at all required for functionality. Your bitline and bitline bar capacitances would be discharged to 0 even when your sense amplifier is not there, but only it will be done at a very low pace. That is the only disadvantage of discharging it with the help of those two NMOS transistors. So that was the use of the sense amplifier. We also had a pre-charge circuitry which kind of pre-charges your like BL and BL bar for read process to happen. Then we also looked at this NV SRAM thing, non-volatile SRAM. So in non-volatile SRAM, what we saw was they just kind of use two other non-volatile elements. That non-volatile element can be your Sonos. So here they place one Sonos, which is non-volatile, and here also they place one Sonos. And these Sonos memories are programmed at the same time as this SRAM cell, so that once you power off this SRAM cell, when you power it on, you do not have to go to the main memory to fetch this data and again go for wake up. So wake up time can be very low in this scenario. And we also saw and discussed why the emerging non-volatile memories could be potential candidates to replace this Sonos in a NVSRAM. So that kind of finished our first module on SRAM cells. So in the assignment, I have asked you to kind of go through what are the major limitations of this RSNM, HSNM. Like we have measured it by kind of sweeping the voltage at these internal load potentials or storage nodes. However, this is not accessible in commercial SRAM banks. So how industries kind of go about it using non-invasive techniques or non-destructive read and all those things that are given in the assignment. And also there is one more method which is called N-curve method. So in that N-curve method, using just a single measurement, you can find all these things. You can find the you can find the RSNM and all these things just by using a single measurement. But even in N-curve method, you have to access these storage nodes. So to mitigate that, what industries are using, that is kind of also a part of your assignment. Okay, with this kind of background on SRAM, now we are ready to go into this field, dive into this field of DRAMs. And DRAM is nothing but dynamic RAM. So why is it called dynamic? We'll discuss that later. So first, let us see what exactly is the market of this DRAM. Why is it important to read about this DRAM? So if you look at the 2020 financial year's memory market, you'll observe that DRAM kind of occupies 53% of the entire memory market. So 53% of the market is like DRAM, flash is 45%, others are only 2%. But this is of 2020. In 2025, things are going to change because these emerging non-volatile memories are going to capture a large amount of this memory market. But anyways, for the time being, last year, this was the scenario, 53% of the memory market was grabbed by this DRAM. And if you look at the major market players, you'll see that almost 95% things are captured by this Micron, SK Hynix and Samsung. If you include Nanya, it's close to like 98%. So these three market players kind of control the entire DRAM market. And where can you see this DRAM? So your main memory is the DRAM. Or whatever RAM you talk about in your PC, in your mobile or whatever, that is actually your DRAM. So if you look at the capacity that you demand for different applications, for server in 2018, so this orange represents 2018 requirement, your yellow represents 2024, that is projected value, but we have reached to this value in 2020 itself. So how, let us see this. So for servers, you actually needed 128 GB kind of a RAM. And in 2024, you can need, let's say, 1 TB kind of RAM. For smartphones, in 2018, the maximum that you could get was 4 GB. Now you can get up to 8 GBs, or nowadays, there are phones which are also coming with 10 GB or 12 GB of RAM. So here, whatever was projected in 2024, which was 8 GB of RAM, you already have it in the market right now. For PC, In general, you would like to have at least 8 GB to 16 GB of RAM. So this was projected in 2018 where they had 8 GB. Nowadays, mostly PCs come with 16 GB RAM, which you see over here. A very drastic change is going to come in the vehicle market. Why so? Because initially you just needed these DRAMs to store some kind of very small information. But now with these automated cars and all this information about GPS and all, like if you want to store this in the vehicle itself, for automated cars this is going to be a necessity. So the kind of capacity of this DRAM or memory inside your vehicles have to be increased considerably. So that is what is being represented by this. Now let me discuss what exactly is a dynamic RAM. I mean, why do we call it a dynamic RAM? So in static RAMs, we used to store the data on the bistable elements. However, in dynamic RAMs, we store the data as charge on a capacitor. Now, since it is being stored as a charge on a capacitor, and nothing is leakage free in this world. So even the transistors that you have, they have got some kind of subthreshold leakage even when they are off. So they have some finite off-state current, and that off-state current has increased because of short channel effects. So you have that leakage. So whatever charge you store on a capacitor, it's continuously being drained, and when it is being drained, what you have is charge leakage. So because of this charge leakage, you start with storing some value which you call 1 on the capacitor, but because of this leakage over a period of time, it switches to a value which corresponds to logic 0. So that way, because of this leakage of charge, it is called dynamic because your states are changing dynamically. And what you need to do is, in order to ensure that this remains at 1 despite the leakage, you have to perform an operation which is called refresh. So let me just highlight this with a different color. So need to perform an operation which is called refresh. So what exactly is refresh? In refresh, first you read the state and then you write it again. Let's say there is a capacitor over here which is storing kind of your state of this memory. It was charged to, let's say, VDD. After some amount of time, it lost some amount of charge because of leakage, and now it is charged to VDD minus VT. Let's say VDD minus Vx. So Vx is the voltage that it lost because of leakage and all. So now what you need to do is every constant period which is in some millisecond, let's say 1 millisecond, which is called the refresh rate or refresh time. So what you need to do, every 1 millisecond, after every 1 millisecond, you need to read the state of here. You need to read the voltage that is being stored here. Let's say it was VDD minus Vx. So just by reading, you will know that it was a state 1. So then what you do is, once you know the state, that it was at 1, then you write 1 again. So you again write 1 to it, so that this charge again becomes VDD, or the voltage again becomes VDD. So you kind of replenish the charge after every refresh period, or at a rate which is called refresh. So in your dynamic RAMs, you refresh the charge on this load capacitor after every 1 millisecond. Okay, so with this introduction to this dynamic RAMs and why they're called dynamic, let me go ahead and talk about the simplest of this DRAM cell, which is this 3D dynamic, which is called 3D dynamic RAM. So this was first DRAM, which was kind of brought in industrial use. First DRAM to be brought to industrial use, and the best part was this was done in 1970 itself. So you can imagine in 1970 itself, Intel kind of came up with this first DRAM. So Intel was so advanced that it came with the first DRAM, which was kind of a 3D DRAM based cell. Now, if you look at it closely, doesn't it look like your 8T SRAM cell that we discussed? Remember there we had two different word lines, one for read, one for write. There we had this this kind of circuit for performing read, and we told that okay, here the read is decoupled from write. Okay, even if you don't remember it, let me just go about it. So first, let us see how we can write anything in this cell, in 3D DRAM cell. So in 3D DRAM cell, you have this 3 transistors, and you have this load capacitor CS. So first, let me define what exactly is CS. CS need not be an external cap. So in 3D DRAM cell, CS can be input gate capacitance plus your parasitics that this node sees. So what are those parasitics? It's this capacitor, it's CG, like this CGG is already there. It would be this capacitor, CGD of M1, and you know it would be several other interconnect. Like if these interconnects are also leading to some small capacitances, so your CS would be kind of then sum of your CGG plus CGD of M1. So the CGG would be of M2 and plus your interconnect parasitics. Okay, so this is the first point that you need to understand, that here we don't need an external cap. This is kind of the node capacitance that this internal node X sees. Okay, now let me remove this. Yeah. Now let us look at the write operation in this kind of cell. So let us look at the write operation. So its operation is kind of similar to your SRAM. So what we do is we assert this write word line high. So we assert this high. And then this BL1. So first, let me write the steps. So first we don't assert word line high. First what we do is we put the value which we want to write on BL1. So BL1 is kind of, you know, your write bit line, the bit line with the help of which you are writing it. So it's similar to the write bit line that you had in your 8T SRAM cells. So let us say you wanted to write a value 1. So what you will do is, here there will be this CBL1. You will kind of put a VDD over here, right? Now this node is VDD. The second step that you do is you assert your word line, write word line high. Okay. Now the thing which now the thing is, how much voltage should you provide on this write word line? Should it be VDD or should it be more than that? So the thing is, if it is only VDD, M1 will pass VDD minus VTH of M1, right? Because NMOS doesn't pass a perfect VDD. It only passes, you know, VDD minus VTH. So what we should do? So what we should do is we should use a concept which is called bootstrapping. So bootstrapping has different connotations or different, you know, implications while applying voltages and while making layouts. So let me first talk about the reference from a perspective of voltage, applying voltage. So bootstrapping means you apply a voltage of VDD plus this VTHN to your write word line, so that it passes what? It passes a perfect VDD. This is what it means. Like, it means you are applying a voltage which is more than the supply voltage of this circuit to the word line. So how can you get this voltage which is higher than the supply voltage on any circuit? So you have this circuitry which is known as charge pump. There are different forms of charge pump. There is this Dixon charge pump, which is most commonly used. So you can use any of these charge pump circuitries to achieve a voltage on the chip which is higher than VDD. So whenever you want a voltage on the chip which is higher than VDD, 2 VDD, 3 VDD, whatever you want, or VDD plus VTH, you can always use this circuitry which is called charge pump. So Dixon charge pump is the most common charge pump that they use. Okay. However, this bootstrapping has a different meaning when you are making layouts of the cell. So while making layouts in analog domain, you have these different metal layers. Let's call metal layer 1, which is at the lowest. Then just above this is metal layer 2. Let us represent it by this. M2. Then let us say we have another metal layer, which is M3. So the resistance of M1 is highest, M2 is lowest, and M3 is least. It goes in that order, generally. So now, let us say that I have two devices at the bottom, which are kind of, connected by this M1. If they are connected by M1, if I apply a VDD to this device, what reaches till this second device is, since there is this line resistance of this M1, across this also there will be some voltage drop. So what reaches over here is VDD minus, let's say, Vx, where Vx is the drop across this line resistance of M1. So just to remove this, just to mitigate the impact of this series resistance, what people do is, so this was kind of the top view. I mean, you are looking at it from the top. Now let me draw, the side view. So from side view, if you see, let's say if this is your transistor level. So that immediately after transistor level, you have this metal one connecting these several transistors. Something like this. Then there is this interlayer dielectric, which is called ILD. And then you have your metal 2. Now your metal 2 goes in a different direction. So how? Let me tell you. So if your M1 is going in, if you are routing M1 in this direction, in horizontal direction, like if you look from top, if you are routing M1 like this, your M2 will be routed like this, perpendicular to this. So in this side view, if you have M1 going in this direction, you will have M2 coming out of the page or going into the page, something like this. Now on top of this, again you have some interlayer dielectric, ILD, and then you have this metal 3, which again, goes in the same direction. This also goes in this direction. So metal 3 also, you route along this direction itself. Okay, now with this kind of understanding, let me tell you what is called bootstrapping. So in bootstrapping, what people do is, they kind of place a via like this. They place a via like this, connecting your M1 to M3. So this via is kind of connecting your M1 to M3. And what it does is, it kind of alters the path of the current. So now, since M3 is having lower series resistance, so now the current flows actually like this. So you kind of avoid this series resistance of M1. So the series resistance of M1 is kind of avoided when you bootstrap this. So this is called bootstrapping of M1 with the help of M3. So this is also kind of general practice, which is done in many of the RF circuits. Okay, so I digress a lot from what I was actually going to talk, but this is also an important concept that people should know. So okay, so we kind of discussed about this write operation. No, still we need to discuss it. So as I told you, what happens here is, you have this access transistor like this, and you have this node X. Let's say this node is called your X, and you have your capacitor, which is kind of your nothing but input gate capacitance of this transistor, and then again you have this another transistor. This is your bit line 1, which I called as the write bit line. This is connected to your write word line. This is something which is connected to your read word line. Sorry. and this is connected to your bit line 2, which is what I'll call read bit line. So okay, during the write process, we kind of applied, let's say this node X did not have any charge. I mean, this was initially at 0. This did not 0 actually. So there is also a point here. So this cell is inverting. How that also I'll explain. So here this node X, let's say it was uncharged initially. So it was grounded. This potential was 0 initially. So it was grounded initially. Now what we did was, we applied a VDD over this VBL1, and then we asserted this right word line high by bootstrapping it to this value, so that it passes a VDD minus. So it passes a perfect VDD, not VDD minus VDH. So now it will charge, right? So it will charge through this. So the potential here at node X now becomes VDD. If you have bootstrapped WWL, well, I mean, if you have bootstrapped right word line, it will charge it to VDD. Okay, so this is how you store 1. Not 1 exactly. So let me go ahead and tell you how exactly it's 1 or 0 in this case. But that is how you kind of charge it to VDD. And similarly, if this were ground and you asserted this high, then it would discharge it to ground. So this is how you can write into this cell. So this write part is kind of decoupled from the read part, like 80 SLABs. Now let us take the case of how you can read it. Let's say now this potential is VDD and you want to read it. So during read, what we'll do is, first we will pre-charge BL2, which we also call the read bit line. So we have this capacitor over here, which is CBL2. What we do is we pre-charge it to VDD. And now what we do, we assert this read word line high. So we turn this to VDD or VDD plus VTHL, whatever you want. So then if we turn this on, so what we have is, you have this transistor which is on now. It is on. And now depending upon whether this node X is at VDD or ground, this transistor will turn on or off. So here, since we stored a VDD on this node X, so this transistor will be turned on. So there would be this path towards ground, and your capacitor, which was pre-charged to VDD, will kind of discharge through it. So then if your voltage at this CBL2 is reducing from VDD, you can use a sense amplifier and you can kind of go to the ground, like you can go very quickly to the ground potential. However, you only have this BL2 which is changing over here. So your sense amplifier has to be single-ended. So your sensing here has to be single-ended. However, here also if you notice, it's not required for functionality. So even if the sense amplifier were not there, this NMOS over here would be turned on, it would be draining this charge continuously, and it would drain this CBL2 to ground, irrespective of whether you have sense amplifier or not. So sense amplifier here also has the role of just accelerating your read process. Okay, now with this discussion, let us kind of point out what can be the advantages of this. And also one more thing, I mean, why I was not telling that if you charge this to 1, it is logic state 1. That is also something which is very important. So if you charge this node to VDD, then you see that there is a discharging path of CBL2 to ground. So what the output will read is 0. So if your X node is charged to VDD, the output will read as 0. And if this X node was charged to ground, if this were charged to ground, this will turn off. So there won't be any conduction beyond this point. and this node will remain at VDD. So your output will remain at VDD, and this will be called logic 1. So this is why this cell is called inverting cell. Why it is called inverting cell? You write a VDD, your output logic is 0, or what you read is 0. You write a 1, like you write a ground to this VX, your output is read as VDD or 1. So whatever you store on the internal node, it's the opposite which the read value gives you. So that is why it is called inverting cell. Now if you look at its advantages. First, there are 3 transistors. So it is denser than SRAM. Okay, this is the first. Second, you have read and write paths decoupled. Do we need to size it? So similar to 80 SRAM cell, we don't need to, we don't have any sizing constraint. You don't need to size anything. Okay, these are the 2 advantages. Third advantage, this capacitance over here, let's call this CS. CS is not an external capacitance. So you can miniaturize these transistors. That is, you can scale them up without worrying about whether this load capacitance is getting scaled or not. I mean, whether you can scale this load capacitance or not. You just scale down these transistors, that capacitance will scale down. So these are some advantages of this 3D DRAM. Although this was very primitive kind of 3D DRAM, I mean, this structure was very primitive. It was only used in 1970s and all. So after this, Dennard actually, Dennard scaling law, if you remember from your device course. So there's this Dennard scaling law. Robert Dennard, who actually proposed the scaling law, he only proposed the first 1 transistor, 1 capacitor DRAM. And once he proposed it, the industry was revolutionized. This DRAM industry was revolutionized. And after that, people stopped using this 3D DRAM. But again, the benefit of this is your read and write is decoupled. So there's no sizing constraint. And also one more important point, once there is no sizing constraint, this charge over here gets disturbed only via leakage. It's not disturbed during the read process. So here also it's non-destructive read. So this is also an advantage of this 3D DRAM. It's still used in some of the embedded applications. Let me tell you that. It's not that 1T1C is used everywhere. This also has got some application. Even now it is being used and manufactured in some embedded applications. Okay. Now what could be the disadvantages? So it will have the same disadvantage that we talked about, the 80 SRAM cell. Since you have different bit lines for read and write, you have different word lines for reading and writing process. So that would lead to a routing complexity. Okay. But that is not very much here because you don't have to work with bit line and bit line bar, and again a word line, again a bit line for just reading the cell, like 80 SRAM cell. Okay, with that, let us just finish this discussion over here, and let us go to this most advanced form of this DRAM, which you have in all these memory devices nowadays, like all the memory, whatever RAM you have in your system. That is called 1T1C DRAM cell, or 1 transistor, 1 capacitor DRAM cell. So here what they do is they just kind of merge these 2 word lines together, WWL and RWL together, and they merge this bit line 1 and bit line 2 together. So if you merge these 2 bit lines and these 2 word lines together, it does give you a benefit of density. So now you only have 1 transistor. However, you have 1 capacitor which is not intrinsic capacitor like the previous case. It's an external gap, or it's an extrinsic gap, which you have to realize on top of this transistor. There you did not worry, you need not worry about the how you were to realize that capacitor. It was simply the gate capacitor plus the parasitics. Here you need to worry about this capacitor, because here this is kind of extrinsic. I mean, why you need to worry about this capacitor? We'll discuss that as well. Okay. So in terms of density, you gain a lot, because now you only have one transistor, one capacitor, and you only have one word line and one bit line. But what you lose, as I told you, VLSI is like life. Nothing comes for free. So here what you lose is, you lose kind of on this read operation. So here read is destructive. So I'll discuss about all these things in a while. So let me first tell you that, as I also told you just immediately before this, that it was kind of proposed by Dennard in 1968, and it kind of revolutionized the way people look at DRAMs. Okay, so now let us look at the write operation over here. So for write, let us write the steps. So first, what we'll do is we kind of put whatever value we want to store in this cell on this BL. So put BL value at what you want to store. Let's say here also we want to store a VDD first. I mean, we want to store this VDD on this CS. So let us do that. And then second step, what we'll do, we'll assert word line high. Here also, if you bootstrap your word line high to VDD plus VTH, you'll kind of end up having your entire VDD being transferred to this CS. So now the value of this CS, or the node potential over here, is VDD immediately after this write. Okay, this is how you write into this node. Now let's say we want to read it. So for reading, what we do is we first recharge our CBL. Let's say the CBL is over here, we precharge it. So in your SRAM or even in your 3T DRAM, what we did was we precharged it to VDD. But here we don't precharge it to VDD. We precharge this to only VDD by 2 to half the value. Even in SRAM, you saw that if you precharged it to VDD by 2, it kind of saves a lot in terms of your CR was not required. The VQ would not even go beyond this VM of the inverter, and you won't have any time the read disturbance. So VDD by 2 is something that you can precharge your this line to, and that is something which people essentially do in DRAMs. So 1T 1C DRAMs, people kind of precharge it to VDD by 2 only. Okay, so you precharge this to VPre, which is generally VDD by 2. But in general, we define it as VPre. Okay, now let us say that the voltage at this CS was Vs. Before before you applied this precharge or anything, the value of this voltage which was stored on CS, let us call that Vs. Okay. So once you precharge the CBL to VDD by 2, the next step is again you assert the word line high, right, for the read operation to complete. So now let us look at the picture more closely. So you have this CBL. You have this M1 which is kind of acting like a switch, and you have this CS, and then you have this potential at Vs initially, you have this potential at V precharge, and now when you are asserting this word line high, you kind of turn the switch on. So the next situation would be something like this. Once you turn it on, you leave it for some time. What would happen? So this would, charge sharing would happen between the capacitors. and this will kind of rest at a common potential, the potential which is common to both, right? So how can we find how much the voltage dropped here or dropped here? So what remains conserved in these cases? What is the quantity that remains conserved? Charge, right? So let me not write Q because Q here can also mean Q and Q bar. So let me write directly charge. So charge has to be conserved. So let us write the charge equations for both the cases. So for the first case, and for the left case, what was the charge, total charge? It was CBL into V3 plus Vs times Cs, right? And on the right hand side, what was the total charge? It would be equal to Vc times CBL plus Cs, right? This would be the total, this would be the charge balance equation, if you say so. Now, if you solve it, you'll find that Vc is nothing but CBL times V3 plus Vs into Cs divided by CBL plus Cs, right? So the voltage at this CBL, by how much it changed, that is what we are more interested in, right? Because we are sensing this bit line. So this del V of how much it changed would be Vc minus V3, right? That is the charge, that is kind of the change in this voltage of your bit line. Let's call this bit line VB. Okay. So you do this, so that would be how much? Vc minus this. So it would be simply CBL times V3 plus Vs times Cs minus V3 times CBL minus V3 times Cs divided by CBL plus this Cs, right? Now you get these things cancelled, right? So if you write it like this, so the change in the bit line voltage because of this is kind of what? It's your, if you take Cs common over there, so it's Cs by CBL plus Cs multiplied by this Vs minus V3. Okay. So this is the change in the bit line voltage, which your sense amplifier has to detect. I'll come to that later, but first let me explain the importance of this term over here. So this ratio of your capacitance value of the external cap that you attach with this one transistor divided by your CBL plus Cs, this is called charge transfer ratio. In general, you have the value of this Cs as 1% to 10% of your CBL. I told you CBL is a large cap, it's in picofarad, and the the capacitances that you can kind of realize with your elements present in your circuit, like your gate capacitance of your MOSFET, or even you have your MIM cap or MOSFET or anything like that, or MOM cap. Even with those, the kind of the range of capacitances that you can kind of get is only in some femtofarads, maybe some 100 femtofarads, but you get only this kind of range, at the max of this CS, which you can realize using monolithic integration techniques. However, CBL is kind of in some picofarads. So any day you have the ratio of CS to CBL as 1% to 10%, and you see this del VBL is only some percentage of this Vs minus V3. So for current technology nodes, your del VBL or the change in the VBL is only in some 100 millivolts. So there is only this much amount of change in your bit line voltage. So here your bit line voltage kind of settles at a value It cannot be changed further because of this charge sharing, and the voltage reduction there is only 100 millivolts. So if it were VDD by 2 earlier, now it will be VDD by 2 minus this 100 millivolts. It won't go to ground. It won't go to ground because there is no discharging mechanism that is being continued, unlike your 3T DRAM or SRAM. So here you need a sense amplifier to pull this to ground for functionality. Here you are not talking about speed. Here you are not accelerating it. It will kind of settle at this value, which is much higher than ground. So if you don't have a sense amplifier, which kind of amplifies this difference and pull this to the ground terminal, you won't ever reach ground with this 1T1C DRAM. So here, sense amplifier is not a fashion, it's a necessity. This is something we should understand. Okay. Also, if you look at your CS, after the read process, its voltage also changes to VC. So its voltage also changes to VC, and its voltage changes by VS minus VC, right? This is the change in voltage on the load cap. So after your read, voltage on the load capacitor changes and it settles at that value. This is called destructive read. So you kind of change the voltage that you had at this load capacitor. So what you need to do here is you need to refresh it. How you refresh it? You apply a pulse periodically. General refresh times are 1 millisecond. You provide a pulse periodically. So refresh is a process where you read the state of cell. If it were 0 earlier, you have to write 0. If it were 1 earlier, you have to write a 1. So it's read followed by write. Read the state and write the same state on that load capacitor again, so that charge is replenished. And this is what gives it dynamic behavior. And hence the name DRAM. Hope this is clear now. Okay. So now let us look at the problems with this. First problem, external cap is required. So this external cap is kind of, if it is monolithically integrated with the help of, let's say, if it is a MIM cap or a MOS cap or a MOSFET, anything, then its magnitude is very small as compared to your CBL. And to have a large change in your BBL, you want this term to be as large as possible. And for that, you want CS to be as close to CBL as possible. You want CS to be as large as possible. So the first research direction in 1T1C DRAM is people are on a quest to kind of find a solution for this monolithic capacitor whose value is large, but at the same time, area is less. So this is one direction where the research has been going on since 1970s. Okay. So this is the first problem with this. Now, second problem, you have a destructive read. So a lot of energy goes in refreshing your charge content. And you cannot work at a very high frequencies just because of this limitation. If you kind of, read and write continuously, I mean, if you are reading it, like if you stored something and then you are reading it up at a very high frequency, you won't get enough time to replenish the charge, to refresh it, and then the state of the memory will change. You will start at value which is 1. When you read it, you lose some charge from it. If you read it like thrice or like 4 times or 5 times, you will kind of induce a state 0, and then you start reading a wrong value. So you have to refresh it after every read or write cycle. After every read cycle, because read is destructive. And during refresh, what you do, you read the state of the device and then you write it back. And one more thing, like in your 3D DRAM, you saw that it was kind of, the cell was inverting. So if you were writing VDD over here, what you read was, let's say if you wrote a VDD on the CX there, or the capacitor, what you wrote was, so let me go back. So if you wrote VDD on the capacitor, output was read as 0. If you wrote a ground to that capacitor, output was read as VDD. What is the case over here? So if you write this as VDD, since your kind of bit line is charged to VDD by 2, so what happens here is, if you are writing VDD and your precharge, V precharge is VDD by 2, so it will kind of again charge this CBL. So if this is the voltage at CBL, which was VDD by 2, if you have written a VDD to CS, this voltage will increase once you start the reading process, and the sense amplifier will take care of this and bring it to logic level VDD. And if you had written a 0 to this CS, then what would happen? The voltage will reduce, and then the sense amplifier will take care of it and will bring it down to ground. So here the sense amplifier is really essential for functionality of this. And here the cell is not inverting. So that also we'll write somewhere. Let's say we'll write here itself that the cell is not inverting. Okay, so we kind of went into the details of this 1T, 1C DRAM, and even your 3D DRAM cell. Now, as I told you, that there is this quest of finding monolithic caps, capacitors with large value but requiring less area, because you are always worried about density, right? You're always worried about density. And at the same time, this also hinders scaling of this CS. So there I told in 3D DRAM, you scale down this kind of MOSFETs, your CS will scale down, and there won't be any problem because there is no destructive read. In 1T, 1C, what you have is, you scale down your CS, you reduce the value, you scale down the technology, reduce the value of CS. What happens is, this charge transfer ratio reduces. And because of that, there would be even lesser kind of transition on this bit line, or the bit line voltage will drop even lower if you have a very low charge transfer ratio. So this CS is also hindering scaling of this 1T, 1C, scaling of 1T, 1C. Because if you're scaling down the technology nodes, your CS is reducing, and as such, your charge transfer ratio is reducing, and the voltage at the bit line doesn't change much. It remains at bit line itself, VBL itself, our pre-charge value itself, VP itself. As such, you'll have to do a lot of things with sense amplifier. And also, let me tell you that it's a single-ended sensing. So converting it into a differential kind of thing, and all sorts of peripheral circuitry magic, I would say, is also very difficult. Okay, so what is the research direction? You have to find a capacitor with large value, but requiring a less area. So there were several kind of innovations. One of the innovation is here, which is known as trench capacitor. So what exactly is a trench capacitor? You dig down a hole in the substrate, and then you have this first electrode, you have this dielectric, and then you have the second electrode. So you have something like this. So what is the benefit of this? Benefit of this is your capacitance is epsilon A by D, right? Increase your area, your capacitor increases. So you can go very deep. You can dig down, trenches with high aspect ratio. So in general, what is the process used for it? So you must have done in the IC fabrication. What is the process for it? Okay, dry etching is there, but what exactly in the dry etching process? Think about it. I mean, fine, what is the process, or which fabrication process is used for realizing deep trenches? By deep trenches, I mean with high aspect ratio. So the main idea behind this is increase the area, capacitance increases. So now the area, effective area is this. You see, the effective area is this. So your area increases, and as such your capacitance increases. Second way to do this is what is shown here. This is called stacked capacitor design. So here you are getting deep into the substrate. I mean, if this was the substrate, we were etching the substrate and getting deeper. Here what we are doing is, if this is the substrate, this, let us say, is our transistor or anything for 1T. Let's say this is transistor. You have gate, source, and drain. So on top of your source, what they're doing is they're now going up and realizing different capacitances in parallel, like this. So here you have, this is going in forward direction, like in upward direction, making kind of multiple floors on top of your transistor. And here you are digging deep and making basements. Here also you are making different capacitors in parallel, stacking them up, and you are increasing capacitance by that. Here you are kind of increasing the area by digging deep and laying your capacitor like this in a wavy form. So both ways you are kind of increasing the area without increasing the footprint. I mean, the footprint on the substrate remains the same of one transistor. Here you are kind of increasing some area requirement on the substrate, but here you don't kind of increase the footprint on the substrate. You are going in a vertical direction. However, these two processes are very complex. These are very complex processes and fancy also. But nowadays, trench capacitors are commonly used in 1T DRAM. So still, there is a need of finding out a way to kind of have a monolithic gap with large value, but not a very large area. So that is still an ongoing question. Okay, and one more thing is there, that this trench capacitor 1T DRAM. So this has got an entirely different technology as compared to your logic technology. So if you remember, I once discussed that your DRAM technology is different. As compared to your logic technology. This is the reason. You have capacitors realized in the form of trench. This is something which is not available in your logic technology, because in logic circuitries, you have to work with very small kind of capacitances, which you can realize using MOSFET, min caps, or anything. But in DRAMs, you have different kind of technologies that you need to have in order to realize a good DRAM. So with this, I would like to conclude this session, And this kind of brings end to the first lecture on this DRAM. In the next lecture, we would be looking at how you can convert this single-ended single-ended DRAM to a dual-ended kind of thing or a differential kind of configuration. And we'll also look at how we kind of provide interface, input-output interface to this DRAM. Okay, thank you so much.